Okay, that's great. We will start. We are doing quadratic residues. Um, okay, so as a basic sort of intro, what we usually do in T is we take some equation, we have some equation E, and we want to get its roots. And this is not like it could be maybe it could be a polynomial, it could be anything, it could be exponential, it could be literally anything. But what we do is we want to consider it mod p, and then we look at how many solutions it has. And till now, um, we what we can do is solve linear equations mod p. So if we have ax plus b is like 0 mod p, then you know that x is minus b by a. This is okay. This is not really useful because you can also solve this without mod p. But what is more useful is when we have divisibility conditions, right? So maybe if p divides ax plus b, then what do you do over reals? You don't do anything over reals. You have to work mod p. So similarly, we want to generalize this from linears to quadratics, or maybe not just quadratics, maybe just cubics or polynomials or anything like that, right? So yes, mod p. This is the equation that sort of motivates this entire chapter. Um, yeah, so okay, at face value, we don't really know what to do, right? We have not seen x squared before, but we know that a quadratic can have at most two solutions. So okay, that is easy to prove. We can prove that at most two solutions exist. The way we do that is, suppose there are like three solutions. We have x, y, and z, which are all distinct. Um, then we have x squared congruent to y squared congruent to z squared mod p. And then this implies that x is plus minus y is plus minus z. But then we know that x and y are distinct, so this plus cannot happen. Okay, maybe I use a different color. This plus can also not happen. So we get x is minus y is minus z, which implies that x is z mod b. Right. So, okay, we know that there are two distinct solutions, and this is also generalized to some extent. Um, uh, a polynomial can have at most n number of solutions, even mod p, where n is the degree. But okay, we will not discuss that here. We may look at that later. Right. So now what we want to do, okay, now here's sort of the first big lemma or theorem or whatever. Right. There are what we define, we called A is a QR. QR is like QR stands for quadratic residue.
Riddhiman,
Yes.
I think they have a question in the chat.
Oh, okay. I forgot to mention, but if possible, don't use chat because I can't really see it while writing. Y plus
Okay.
cannot happen. Oh, okay. Yeah, we are looking at distinct solutions mod P, right? So if these all are distinct, then if all of them are distinct, then x cannot be congruent to y mod p, right? We want to look at distinct solutions. Oh no, no, we want to look at distinct solutions mod p. Does that make sense? Yeah, we want to look at distinct solutions mod p. So x has to be minus y and y has to be minus z. So from there we get that x and z have to be the same, which is uh, contradictory to what we assume. Yes, let's move on. The first big lemma, right? We define A to be a quadratic residue, which we will just call QR in short. If there exists, oh, if there exists X such that P divides, or rather X squared is congruent to A mod P, and NQR otherwise. So the idea is that the number of QRs is equal to the number of NQRs is equal to P minus 1 by 2. Also, by the way, usually in this definition we exclude 0. You will see why. But yes, that's why we have P minus 1 by 2 plus P minus 1 by 2 equal to P minus 1 and not P. Yeah, let's continue. Okay, so how do we do this? This is sort of surprising because there is, I mean, if you look at maybe cubes of power, if you look at like x to the power 4, then this just does not happen. That is, there's a reason why this number 2 is special. Um, so what you do for, okay, do I let you try to prove this? Or shall I just show you the proof? Okay, wait, just okay, yeah, sorry for that. Okay, we will just show the proof. Fine. I'm assuming, okay, just how many of you have already covered these things? Maybe you can type in chat or, oh yeah, sure, you can raise hand. Shall I give you a bonus problem? Okay, somebody wants to try. Okay, yeah, sure, you can try. I will give you a bonus problem in the meanwhile. Hold on. Um, one do I give? Um, yes. Those who have already seen quadratic residues earlier, you can try this.
Sorry, what did you write as the expression? Uh, is that like floor of root JP?
Yes.
Okay.
Uh, okay, so I will just give you the proof. And the idea is to consider this set. Okay, so by the way, there are like two proofs. Are you all comfortable with primitive roots? Yes, okay. So you can do primitive root set. That is sort of a more straightforward proof. There is another proof which does not require you to know primitive roots, but it's less generalizable. As in it's only true for n equal for this two and not for three or four or something like that. Okay, I think the primitive root one is more um it's more straightforward. So consider this is a set of all numbers, right? Let G be a primitive root. So G 1 G squared. Okay, G to the P minus 1. Does this make sense? Okay. And then after that, you can observe that if x squared is congruent to A mod P, and if you say x is congruent to G to the power P, and A is congruent to G to the power R, then we will get G to the power 2T minus R is congruent to 1 mod P. This implies that P minus 1 divides 2T minus R and 2. Okay, so I might not have mentioned. Yeah, all of this is for odd primes. We do not include 2. So this implies that 2 divides R, right? And vice versa. So if x squared is not x squared congruent to A mod P has 0 solutions, has no solution, then if we let A is equal A to be G to the power R, and R is even, if R is equal to 2R dash, then we know that G to the power R dash squared is just A mod P, which is contradictory, right? We know it does not have any solutions. Okay, so this implies that I'll just write it here. A is a QR. QR is the same as saying that A is just G to the power some even number. Right. And then from there, you can show that the number of indices which are odd is the same as number of indices which are even. So we are done. Oh, somebody wants to see the bonus now. Here, this is the bonus problem. You can take a screenshot. Okay, I will move on. The other proof. Okay. The other proof is to take the set 1 squared, 2 squared, dot dot dot, p minus 1 by 2 the whole squared, and show that this is indeed all the QRs. I mean, if you understand the primitive root solution, you can complete this on your own. So I will just, you can try this after the class. I will not be going here. Anyways, what's next? Yeah, so we can already do some pretty good stuff. Okay, let's look at the problem. Um, uh, this is, hold on. Oh yeah, this is, yeah, INMO. Uh, um, yes. Right, so we can already solve problems like this. I will, okay, I'll give maybe 5 minutes for you to try this. Is that okay? Residue classes just remainders. Okay, so if anybody has any ideas, you can share. Um, mm, okay, shall I start with the solution, or do you need more time? Okay, sure. I'll wait for maybe 2 more minutes.
I think I'm done with the problem p square minus 1 by 12. Can I get another one?
Okay. If you want, you can DM me your solution or write it.
Sure.
Okay, hold on. I will give you another problem. Yeah. Uh, mm, okay. Um. Okay. Let's see. Oh, okay. Oh, okay. Let me give you this problem.
Is it exact number of solutions or at least this many solutions?
Exact.
Okay.
Okay. Gee, hmm. Okay. Uh, I I okay. This is probably a typo, but it is QR into QR is NQR, and it's not that. In fact, we can do this without that. Okay. So solution. I will come back to this for a second solution, which uh, but I think this solution is more straightforward. So take some C. And we want to, okay, wait, the answer is all, like all the residue classes or all the remainders can be written in this form. And the idea is to take some C such that, and we want to look at this equation, right? So what we do is we do this. And now we analyze the LHS and the RHS separately. So A squared, how many? What is the possible residue classes that this can take? It's P minus 1 by 2, right? Because this is just a QR. Plus, we it can also be 0 because 0 squared is 0. And remember, in this we excluded 0 because 0 is not in this primitive root set. Yeah. So here we have to make sure to include 0 back. So we have A squared can take P minus 1 by 2 QRs plus one other solution. This is just like 0 equal to P plus 1 by 2 distinct remainders. Similarly, C minus B squared can also take P minus 1 by 2 plus 1 equal to P plus 1 by 2 distinct remainders, mod P, right? Okay. Yeah. So now, if suppose this equation has no solution, then LHS is never equal to RHS, right? But the point is that if that is the case, then we have P plus 1 by 2 distinct remainders from the LHS and another P plus 1 by 2 distinct remainders from the RHS. That would give us P plus 1 by P plus 1 distinct remainders, which is false. Or you can also think of it this way. By PHP, there has to be some overlap, and that overlap will give us a solution. Does that make sense? Is that clear? Okay, nice. So what we can do, we can just generalize this. You know, the constant here, there's the constant one, which is a bit unnecessary. We can generalize this to showing that, and I will leave this as an exercise. Show that a squared x squared plus. Okay, hold on. Oh yeah, okay. Show that a squared x. It's not a squared. It's ax squared. Oh yeah. Ax squared plus b squared y squared congruent to c mod p has at least one solution x comma y where like a comma b are not zero mod p. I will leave this as an exercise. If you understand the proof for the previous problem, this should be straightforward. Okay, now I will move on. Okay, now what we do is we analyze the product of a quadratic residue and say NQR, right? So, okay, the idea is that if you have a quadratic, if alpha is a QR, this is QR, and beta is a QR, what can you say about alpha beta? Obviously it's a QR, right? Because this is say a squared, this is b squared, so this is just is ab the whole square, right? Mod b. Okay, so we know that QR multiplied by QR is equal to also gives us a QR, right? Okay, what if we change this to an NQR? So alpha is a QR, but beta is an NQR. Okay, so alpha is a QR, we write this as A squared. So what can we say about alpha beta? This is also fairly intuitive. It's going to be an NQR, right? Because for the sake of contradiction, suppose this is like some L squared, then we have beta is congruent to L squared by alpha, and we know that alpha is A squared, so this becomes L by A the whole squared. And this thing is a QR, but we know that beta is an NQR, so that's a contradiction. So, okay, QR, we know that this implies that QR into NQR is not a quadratic reciprocal. Good. Now, what about the third type? What about we have alpha and we have beta. Suppose they are both NQRs. What can we say about them now? Yes, this will be a QR, and this is a bit um. This is why this is why quadratic residues is particularly good, maybe compared to cubic residues or something, because this statement is false. If I change this Q to a C, so like cubic residue or non-cubic residue or something, this statement becomes false. That's kind of why quadratic residue is particularly good. And the idea is that you write it in its primitive root form. So you write this as g to the power a, you write this as g to the power b. And we know that this is NQR, and we did earlier that we know the statement holds true, right? Since it is an NQR, the exponent is going to be odd. So we know that this is odd. We also know that B is odd because beta is an NQR. Yes. Nice. So alpha beta is g to the power a plus b. And we know that this is even because odd plus odd is even. So it is a QR, right? So now we have R is equal to 1, QR. We multiply NQR to the remainder set. Okay, yeah. So the idea is that we can write this as a table, right? This is QR, this is QR, and this is NQ. Right. Yes. Okay, this is too big of a people. Right. We know that QR, this is a sort of a multiplication table. So QR into QR is a QR. That is straightforward. QR into NQR is also an NQR, as we saw. NQR into QR is an NQR, and NQR in. Does this table seem familiar? We have seen this table, right? This is sort of intuitive. If this is the same, we'll get the same. If both of them are opposite, we'll still get the same result. Like we'll still get a QR. The idea is that this is very similar to the multiplication of ones and minus ones, right? So one ones are one, one into minus one, minus one into minus one into one is minus one, and a minus one into minus one is one. Okay, so what we do is we make a function now. So we want to map QRs to one. We have a function f defined on P, defined on mod P, which sends fp of A is equal to 1 if A is a QR, and -1 if A is an NQR. Right. And the whole idea is that this thing, this function f is multiplicative of AB into FP of B. So what we do, so let's bring some standard notation. We don't write FP, we write this is called the legendary symbol of A with respect to P. This is the same definition. So it is 1 if A is a QR and -1 if not. From this, just be careful because this is defined only for A not equal to, not congruent to 0 mod P. Okay, let me see chart. Oh, acha, is this a solution to the bonus problem? Okay. Okay, I'll check that later. Okay, let me see if I can give any problem now based on this. Okay, yeah, we can do the previous problem in another way. Come back to Austria INMO. Yeah. We want to show that A squared plus B squared congruent to C has no solutions, right? That okay, we want to show that it has a solution, so we assume that for some ABC this does not have solution. For some C there is no A and B. The idea, what you do, you have B squared is congruent to C times C minus A squared. So what you do is you write C as L into A squared. Right. And we can do this because L is just C into is just C into A squared ka inverse. So you can just take A squared, you can multiply some L and you will get C. Right. The point is that okay, so from this we get B squared congruent to okay C. Yeah. We get L squared, we get okay, no, wait. This L into A squared minus A squared, which is just L minus 1 into A squared. Right. And we know that C is not itself a quadratic residue, right? Otherwise, if C is QR, then just take like then let A equal to 0 and we will get B squared congruent to C for some B, right? So suppose A is an NQR. Suppose C is an NQR. Then what we know that L is also an NQR because we know that NQR into a QR is an NQR. So this is an NQR, this is an NQR, this is a QR. So this will be an NQ. So L is an NQR, and we know that this has no solutions, right? Because that's what we assumed in the beginning. So from this we can say that L minus 1 is also an NQR. Right. Can you see the issue with this? We have L minus 1 is also an NQR. We have L is also an NQR. So we just keep going forward. But eventually you have to come across a QR, right? Because there are P minus 1 by 2 QRs. You can't just have all NQRs. So eventually you will come to a state where this is a QR. Suppose like T. And then T minus 1 is an NQR. T minus 1 is yes, you will come across like t minus 1 is NQR and t is a QR. So the first time that t is a quadratic residue, right? And then you plug this in here and then you will get the solution for B. So there will always exist some A comma B for C. Does this make sense? Okay, so this solution is a bit more specific to this case, as in you have A squared and B squared and not 2A squared, which would be a bit more difficult to deal with. But yeah, you can solve this in both ways, and ideally you should know both the ways. Okay, let me see if I can. Okay, shall I do some more theory or shall I give a problem? The issue is that we haven't covered the main theory yet, so we might not be able to solve good problems. Oh, okay, okay. Let's just do some theory. Okay, do you want? Okay, I did give another bonus problem. Are you already done with that? The second bonus problem. If you are not done, you can try this one. Oh, acha, you have done it before. Okay, nice. Let me find another problem. Yeah. Okay. Here is bonus three. Um, oh, I didn't even know the. Summation five. I minus one. Okay. By the way, here summation. Here you might see for. Okay, wait. I will just define. Yes. Proof. Proof that if and only if one. Oh, okay. Wait. This is not an. Yeah. This is the third bonus problem. This is mod 8. Okay, let's cover some theory. Uh, uh, quadratic reciprocity. So the idea is that if you're given a random thing here and if you're given a prime here, how do you decide if this is 1 or minus 1? Okay, maybe first we should not do this. Maybe first we should do Euler's theorem. Okay. Yeah. This states that the legendary of A with respect to P is equal to congruent to minus 1 to the power A to the power P minus 1 by 2 mod P. And okay, this is sort of intuitive, as in you just write. Okay, should I give time for you to try this or? Okay, firstly, this will give plus minus 1, right? Do you see that? We know that this is plus minus 1. Yeah, you see that this is plus minus 1. Are you sure that this is plus minus 1? Yes, because like if you write, because this thing cos square is congruent to 1 mod p. So this thing itself is plus or minus 1 mod p. Nice. So you can try this for maybe 3 or 4 minutes. I will be back in like 3 minutes. Okay, let's see. Let's see. Do you have any ideas?
I think you could use the primitive roots again.
Yes, that's correct. You just use primitive roots. So you write A is just like G to the alpha, and then A to the P minus 1 by 2 is just G to the alpha into P minus 1 by 2, right? And if alpha is even, then this quantity is divisible by P minus 1, right? By 2. So this becomes 1. And if alpha is odd, then P minus 1 does not divide this quantity. So in this case, alpha is not equal to the alpha to the power P minus 1 by 2 is not equal to 1. But we know that it is plus or minus 1, right? Because it's something which you square, you get 1. Because a to the p minus 1 is 1. So if this is either plus minus 1, and if it is not 1, it has to be minus 1. So if alpha is even, so if A is a QR, then it's 1, and if A is not a QR, then alpha is odd, so it's minus 1. So yeah, that's essentially it. And this might seem sort of easy to prove, like you just do primitive roots, right? But this is very important, especially when you have to evaluate summations. And we will probably not cover that in today's lecture, but yeah, in upcoming lectures, or maybe just in problems in general, this is just like very important. This nice. So we can move on to quadratic reciprocity. And the point is that if I just give you something random, uh, how do you do this? Do you just try and see if 67 is a perfect square mod 101 or something? What do you do? There's no way you do that, right? That's just too lengthy. You would use Python. Okay, great. I don't think Python is allowed in INMO though. So yeah. Okay. The idea is that this is done using quadratic reciprocity. Why am I writing again? I've already written. Yeah. So the formula goes like this. If P and Q are two odd primes, distinct odd, then this the legendary of P with respect to Q into the legendary of Q with respect to P is minus 1 to the power P minus 1 by 2 times Q minus 1 by 2. This is the most important thing probably in this chapter, because if you have a problem which uses quadratic residues, if it is like decently hard, then it will use this. And the point is that this should also come as a surprise, because we have something mod q, we have p mod q, and we have q mod p, and they are just magically related like this. And this is another thing that is special about taking x squared congruent to a and not x cubed or x to the power 4 congruent to a, because a good close relation between p mod q and q mod p exists here. It does not exist there. Okay, it does exist there, but it's not as clean as this. You need to define lots and lots more stuff. Right. So, I mean, usually we skip this proof, but I don't think we should skip this. Okay, I think we should do this because this is a very interesting and very good proof. Oh. Okay, so before we directly go to this, we start with something known as Eisenstein's lemma. Which is just sort of a new way of evaluating the legend of A with respect to P. Oh, okay. So yes, this is Eisenstein's lemma. Shall I give you some time to try this. It's not, yeah, it's not very easy. I'll. Do you want time to try this, or shall I just tell you the proof? Okay, this will probably require maybe 7-8 minutes. Yeah, this it's a bit of an unmotivated solution, but yeah, you can try this for maybe 6 minutes, maybe 7 minutes. I will be back in. I'll be back in. Okay. Anybody? Any progress? Maybe even just a vague idea of what to do here. Okay. Question: do we use primitive roots here? Do you think primitive roots will help?
No, I don't think so.
Okay. So if we don't do primitive roots, what do we do? I mean that is justified because where is the primitive root here? More okay, maybe here you can put in g to the power p minus 1 by 2. What about this? How do you deal with this? This is like very weird. And it's not even a normal summation, right? It's something like this. It's only even values. How do you do this?
Is the summation only for even values of u or?
It is only for even values of u.
Okay.
P raised to the power q minus 1 by 2. Yes, that is true. Oh, are you trying to prove this directly? Because, I mean, that won't really work. How do you... Because it's like this is mod q and this part is mod p. And they're just different. You can't take mod p and mod q together. Okay, yeah. Don't go for the quadratic reciprocity formula. Try this. Okay, maybe I'll just get started with this proof. So okay, this thing is a bit weird, right? How do you really deal with this? Okay, so what we do is we define R of U is the positive remainder R mod U mod P. Right. It's different from U mod P because if we had something like minus one, that would actually become P minus one. So there is some notion of size, but more than that, there is some notion of divisibility by other numbers, which is usually not the case in mod P because of CRT, right? You can have have anything divisible by anything, and you just add in mod P, and then you just put CRT, and you still have solutions. But the point is that if you restrict it to positive remainders, you can put in some other size conditions or maybe some divisibility conditions. Um, yeah. Okay. So for this, we define two sets. A is minus one. Yeah. Okay, this is the first set, and you can sort of see what we did here. We have R of something even, and even in the summation we had something even divided by P. Okay, this part is a bit confusing, but okay, that will get clarified later. B is just the set of 2, 4, dot 3 minus 1. The set of even residues mod P. Again, we are taking positive residues. 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 We are taking positive residues Nice. So the claim is that A is equal to B. The sets are equal. And okay, motivation. This is very unmotivated. Okay, as I work out this proof, you will realize why this works, and that is sort of magical. I will I will talk about it a bit more after we are finished with this. So what we claim is that A is equal to B, right? Okay, the first thing you see that wait, this is positive remainder. Okay, if R of 2k is even, then this term, this minus 1 to the power of R of 2k into R of 2k, this is also even. Is even. Because this thing just becomes 1, right? And what about if it is odd? Then this thing is still even because we have minus 1 to be something odd times an odd thing. But so this thing becomes a minus 1. So this is congruent to minus odd mod b. But the idea is that we look at positive remainders only. So this will become p minus the odd thing. And now this thing is even because this is odd and this is also odd. So this is even. So this is sort of a very genius way of taking, something which maybe even may not be even and making it always even, right? And I mean, this is quite a common sense. I mean, if you have sort of alternating plus and minus sign, you will put in a minus 1 to the power something in your expression. So what we have shown is that this set has all even, it has all even residues mod p, looking at positive remainders. And this has p minus 1 by 2 elements. All we need to show is that any two elements are just distinct. And then that would imply that the sets are equal. So, okay, how do we do that? Okay, this is the easy part. So now we don't really care about, we don't really care about mod, this minus 1 thing or something. Okay, wait, this is, okay, but yeah. Okay, suppose some minus 1 r to the power minus 1 to the power r of 2k 2 is congruent to minus 1 to the power r of 2l times r of 2l mod p. And this thing is just 2ak, right? Okay, maybe, okay, I will put in the a later. For now, let it just be yeah, this is just 2k minus 1 to the power something is congruent to minus 1 to the power something into 2l mod p, and then you cut the 2's and you have k congruent to plus or minus l mod p. Except here the bounds are that k and l are from like p minus 1 by 2 because we are taking 2k and 2l, and that has to be within 1 to p minus 1, right? So you have k is congruent to plus or minus l mod p, and okay, and from this you can see a contradiction, right? If k is congruent to L mod p, then we are already done. Then they cannot be distinct. And if k plus L is congruent to 0 mod p, so that means p divides k plus L. But observe that because of this size thing, because of this bound, this sum is at most p minus 1 by 2 plus p minus 1 by 2, which is p minus 1. And now this is a contradiction. So indeed, this is just this just proves that no two elements in the set A are equal. So we have p minus 1 by 2 distinct even remainders, and this is also p minus 1 by 2 distinct even remainders. And that's it. So these two sets have to be equal. The idea I want to emphasize here is that you replace in the definition, you put an a here, and everything is just the same. Because this argument, this even odd argument, this does not depend on exactly the definition of R of 2k. And the argument here, the argument to show that they are distinct, we would have a 2k into a, and here also 2l into a. And this would also cancel because a is co-prime with p. So the idea is that this is also something very similar that we did in, yes, exactly, mod chapter 2, proving Wilson's theorem, right? We just multiply by, okay, it was Wilson's, not Wilson's theorem, it was Fermat's little theorem. We just sort of permute the residue class, and then we show that the two sets are still equal. We multiply and things cancel out, right? This is something very similar that we have done, because this part is sort of the permutation part. Nice. So what do we do when we have sets of equal sets? What do we do when we have equal sets? We just multiply, right? So we have the product of S in set A uh, is equal to the product of S in set B. Mod P. And if you write out the products in set A, you will get minus 1 to the power R of 2 plus, okay, I'll just into R of 2 4, and then dot 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 p minus 1, p minus 1. This is the product on the LHS. Okay, we have a question. When would R of 2k be odd? R of 2k, we don't really have control over it. Oh, R of 2k, when we replace it with, where is it? Okay, if R of u is just the remainder of u, if we look at the positive remainder, then it's all fine. But when we put au, then we don't know if it is positive or negative. So we don't know if the remainder is odd or even, right?
Got it.
This is congruent to the elements in set V, that is just 2, 4, dot, 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 p minus 1. And this thing is nothing, just if you just take the minus 1 common, and if you just sum all the powers, plus r of p minus 1. What is this? This is just 2a. This is just 4a mod p. And this is just p minus 1a. So we have, and how many of these do we have? We have p minus 1 by 2. So we get a to the power p minus 1 by 2 times 2 times 4 times dot 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 times p minus 1. Look at this. We cancel this. So from this we get a to the power p minus 1 by 2 is congruent to, you take the reciprocal of this thing, you'll just get the same thing. So you'll just get minus 1 to the power r of 2 plus dot 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 plus r of p minus 1. We are still not done though. And this is just like the legendre of A with respect to P. We are still not done though, because this is not the exact summation, right? The exact summation was some GIF thing, floor thing. How do we do that? Okay, the idea is that suppose you have some 2u, right? This is some even thing which is in here. The idea is that you write it as, we want to write it as something into P plus the remainder. That is why you have the positive remainder, right? So let me ask you, what is this? What is this something? You want to write it in the form of the Euclidean algorithm, right? What do you do? Any ideas? Exactly. You get floor of that. You have the floor of this thing times P plus R of 2U is equal to 2U. But this is sort of why we have evens, because this thing is 0 mod 2, right? This thing is 0 mod 2. So what we end up getting is just that P, the floor, times P is congruent to R of 2U mod 2. Also, by the way, like the minus 1 is the same as plus 1 mod 2. So you can take this on the other side, it will be the same. And we know that this thing is 1 because P is odd. So look at this. And we still want mod 2. We just want only mod 2 because it is in the power of minus 1, right? We don't really care mod anything else. We don't care about its exact value. We just want to see what it is mod 2. So we have, okay, I will just copy this. So we have this thing, and now this is the same as P minus 1 by 2, or the floor of 2U by P, which is exactly what we wanted. So there we go. This is the proof of the Eisenstein's lemma.
Could you just show the last part again? The
You mean this part?
yeah, like yeah.
Yeah. So the idea is that you want to relate this guy to this guy because this guy is in the summation. So you write to you, and this is how you bring in flows, right? If you write it in the form of the Euclidean algorithm, then this is the remainder, and this is a part of the reason why it's the positive remainder. And you have P into something, and that something is just a floor of that. So does this equation make sense?
Yeah.
Yes. So now we just take mod 2 because this guy is divisible by 2. So it's 0 mod 2. So we get that this thing is congruent to this thing mod 2. And then we know that P is just 1 mod 2. So that just vanishes. So we have this thing. Is that okay?
Yeah.
Okay, and then finally we just put it in because we are taking the exponent in the power of minus 1. So we only care mod 2. So this thing is the same as this thing mod 2. So this summation still holds. And that is what we wanted to prove, right? That was the lemma in the beginning.
Yeah.
Okay, good, good. Okay, now you can probably see how this relates to this. As in, we have a minus 1 in the legendary symbol. Okay, I'll just go here. Is equal to minus 1 to the power some summation. I'm not writing that. And we know that the legend of q with respect to p is also minus 1 to the power some summation. So if you take the product, this into this, minus 1 to the power, it's just the addition of these summations. Okay, I will just write. Okay, maybe write INJ. Yes, right. And we want to show that this is a thing we want to show. Or rather, we want to simplify this equation, this expression. You can think of it that way. This is a very bulky expression. It's hard to manipulate, or it's hard to think about this. So how do you exactly simplify this? Any ideas? Okay, this part is probably the most sort of big brain part. And the idea is that you stop thinking, oh, we can try to remove floor. Sure, we can remove floor, but then we'll go back to the remainder thing, right? I mean, yeah, you can try, and there might exist a manipulation, but I'm not really aware of that, and I don't think it's very clean. Okay, the thing I will cover here, and we have only 6 minutes left, so we might go like 5-10 minutes over time. Is that okay? I'll try to finish as soon as possible, but I also don't want to drag this. I don't want to rush this part. Yeah, the idea is that you stop thinking in terms of numbers and now you think in terms of graphs, or rather the coordinate axis. Okay, this is probably where I should import the diagram and not. Oh, okay, wait, just a second. I've not opened. Okay, wait, just a second. Yes. Okay, yeah. Okay, that is too big, maybe. Okay, yeah. The idea is that we think in terms of this coordinate axis, because this summation here, maybe I'll just expand this a bit. Yeah, this summation here, or maybe we just remove this guy. Yes, this summation here is the number of points with even x coordinates under the line, under this line. This is, in our case, we take p equal to 13, just as an example, q equal to 11. So this point is P comma Q. And this summation represents the number of points with even x coordinates under this line. And as to why that is, it is sort of a very genius thing to notice. Okay, let me show you why that is. So if we have any point x comma y, which is under this line. Okay, what is this line? This line is py equal to qx, is it? Yes, py is equal to qx. So rather the slope of this line is y by x is equal to q by p. This is slope. And what is the sort of, okay, this is 2u. So we have a point with some even x coordinate. And what is the slope? What is like the slope of the point of this line joining the origin and the point? It's just y coordinate by x coordinate, right? So that will give us y by 2u. And notice that if this is less than or equal to q by p, then this point sort of lies under the line, right? So okay, so how many? So this just implies that y is less than or equal to 2u q y. Okay, wait just a second. Okay, yeah, sorry for that. Y is less than equal to 2u q by p, but y is an integer, so we take the floor. Does this term look familiar? It's the same term, right? We have 2i. We have like 2i here, we have 2u here, but it's the same term. So from this we okay, how many possible y there are? It's like one y is greater than equal to 1 and less than equal to this summation thing. So if we sum over all u, then we will get this summation, but that also means all the points with even x coordinates. So x coordinate is equal to like 2u as u sums over 1 to p minus 1 by 2, and the y coordinate is such that it lies under the line. So we can see that this thing is same as this thing is indeed the number of points here. Also, by the way, these are not included in the points. The graph is a bit, yeah. Okay, so how do you deal with this? How do you work with this?
You can do the same thing for the other summation also.
Yes, you could try that. But the point is that in that case, the x coordinate gets changed to y coordinate. So it's not as simple as just, doing this. Okay, wait, I'll just black.
Could you just like rotate that part then like and then make it align? I don't know, because like from P comma Q you could go to Q comma P and then you could like rotate it or something.
Oh, acha, are you saying that this is like x equal to y, you reflect this, you reflect the entire grid? Is that what you're saying?
Yeah, something like that.
Yeah, you could absolutely do that. But the issue is that, okay, how do you work from there? That is a good idea. That's a good idea. But it kind of doesn't work because you want to sort of stick to this graph, right? You have like two different coordinate system, like you have two different coordinate boxes in a sense. And then some points overlap and some points don't overlap. So you have to keep track of those as well.
Yeah.
Yeah. So what you do instead is you realize that we do not care about the exact value, right? We only want mod 2 because the entire summation is in the power of okay, it's in the power of -1, right? Here, this entire summation is like in the power of -1. So we only want to evaluate it mod 2. So the idea is that let's remove some things. Okay. Firstly, what is sort of the midpoint of this graph? P minus 1 by 2 comma Q minus 1 by 2, right? So, okay, in our case, that is 6 comma something. Or rather, P, just take P by 2 comma Q by 2. It's just somewhere over here, right? That would be 6.5 comma 11 के लिए 5.5 or something like that. Yeah, somewhere over here-ish. It may not lie on. Will it lie on the line? It will lie on the line. That is fine. But it's somewhere in the middle, right? So what you do is you draw this line and you okay. Yeah, and you only look at these points. And you sort of want to continue the graph over the line as well, right? So what happens if you just sort of mark these points? How many points are there? Okay, so we had 1, 2, 3, 4, 5, 6 points here, and we have 1, 2, 3, 4, 5 points here. 6. Okay. Okay, we have 6 and 5 points, but we sort of want them to be equal mod 2. So what we do is we remove this point. And okay, there's another reason why we are removing the point that will become clear in maybe a few seconds, few minutes. So if you notice, we are taking this sum to q minus 1 by 2, right? 10 is just q minus, not q minus 1 by 2, it's q minus 1, which is even. So you can note that the number of points here and the number of points in this above that, they are equal mod 2, right? So the idea is that you can sort of reflect, not exactly reflect, but you can consider the points above the line, and it won't affect our calculation because it's mod 2, right? So okay, this is complete the thing. It will look something like this. So the point is that yeah, the idea is now what you do, you take these points and you sort of reflect them in the center. Okay, it looks pretty bad. But the idea is that notice that these points, sort of this quadrant has the same area as this quadrant, right? Because it's sort of symmetric about this point. We are just reflecting. And observe that this is sort of a fractional, this is sort of a half integer. So when you reflect in from here to here, the points which had even x coordinate here will go to points which have odd x coordinate here. And because these points were on top of the line, what will happen is that the reflection will be below the line. So something like maybe this point goes to here, and then that point goes to there, and then maybe this point goes to here, and then this, and then this, and then this, and something like that. So now if you look at it, you have earlier you had only the points with even coordinates. Now you have the point with odd coordinate as well, but now you're working with this smaller triangle. This smaller triangle. Okay, so now what you do, you're not constrained, you don't have to really worry about even or odd coordinates. You just have all coordinates, right? Now you do the same thing with q. So now you take the same thing with, you look at the other summation. Well, q, and this becomes q. Now you look at the other summation, and you will get all the points with integer coordinates in this region because it's symmetric. So this entire sum is same as the number of points in the small rectangle. And how many points are there? How many points are there in this small rectangle? We have we have one cylinder p minus 1 by 2. We have one cylinder q minus 1 by 2. So the total number of points here is p minus 1 by 2 into q minus 1 by 2. And we are done. So you replace it in this sum. This is equal to minus. And then you're done. Does that make sense? It's probably it's a bit heavy, especially if you're seeing this for the first time. You might have to maybe rewatch or maybe read it up on wiki or something to understand it fully. But are there any doubts?
Yeah, so like at the end, like when you get that, when you like kind of reflect it or something, like those points,
Yes.
what do you call it? So like the summation you're finding is essentially like that under
It is,
that triangle, right?
yes, it is that, but modulo 2. And we are doing modulo 2 because it's in the power of minus 1. So that's what we care, right? We care about it mod 2.
Got it.
And then when you work out the other guy, this is like p by q, the other guy is q by p, you get the points here. And then the total number of points is just p minus 1 by 2 into q minus 1 by 2. So yeah, that works.
Got it.
Anyways, yeah. Um yeah, anyways, we'll probably end it here. We couldn't do too many problems. There's also some heavy theory left, but this will do for most of the problems that you will encounter. Anyways, yeah, the class is ended. If you want, you can leave. If you have any doubts, you can stay for maybe 2, 3 more minutes. I'll just end the recording. Oh, can you give any handout for the theory? Oh, okay, yeah, yes. I will share something. Uh, I'll share something in the server. I'll also share the solutions to the bonus problems if anybody wants to have a stab at that.